Speaking of solutions, this is the last little bit of thing that you need to know. And that is, this defines a problem, but what we also want to have whenever we have a problem is a solution. So the solution to a Markov decision process is something called a policy. And what a policy does is it's a function that takes in a state and returns an action. In other words, for any given state that you're in, it tells you the action that you should take.
Like as a hint?
No, it just tells you this is the, well, I mean, I suppose you don't have to do it, but the way we think about Markov decision processes is that this is the action that will be taken.
I see. So it's more of an order.
Yes, it's a command.
Okay.
So that's all a policy is. A policy is a solution to a Markov decision process. And there's a special policy, which I'm writing here as policy star, or the optimal policy. And that is the policy that maximizes your long-term expected reward. So of all the policies you could take, of all the decisions you might take, this is the policy that optimizes the amount of reward that you're going to receive or expect to receive over your lifetime.
So like at the end?
Well, yeah, at the end. Or at any given point in time, how much reward you're receiving. From the Markov decision process point of view, there doesn't have to be an end.
Okay. Though in this example, you don't get anything, and then at the end, you get paid off.
Right. Or unpaid off.
Right.
If you fall into the red square. So actually, your question points out something very important here. I mentioned earlier when I talked about the three kinds of learning that the supervised learning and reinforcement learning were sort of similar, except that instead of getting Y's and X's, we were given Y's and X's and Z's. And this is exactly what's happening here. Here, what we would like to have if we wanted to learn a policy is a bunch of SA pairs as training examples. Well, here's the state and the action you should have taken. Here's another state and the action you should have taken, so on and so forth. And then we would learn a function, the policy, that maps states to actions. But what we actually see in the reinforcement learning world, in the Markov decision process world, is we see states, actions, and then the rewards that we received. And so, in fact, this problem of seeing a sequence of states, actions, and rewards is very different from the problem of being told this is the correct action to take, maximize a function, or find a function that maps from states to action. Instead, we say, well, if you're in the state and you take this action, this is the reward that you would see. And then from that, we need to find the optimal action.
So pi star is being the F from that previous slide?
Right.
And R is being Z?
Yes.
And Y is being A?
And S is being X, or X is being S.
Gotcha.
Right.
So, but I'm a little confused about this notion of a policy. So we have the thing that we tried to do to get to the goal was up, up, right, right, right.
Yes.
I don't see how to capture that as a policy.
It's actually fairly straightforward. What a policy would say is, what state are you in? Tell me what action you should take. So the policy basically is this. When you're in the state the start state, the action you should take is up. And it would have a mapping for every state that you might see, whether it's this state, 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 or even these two states, and it would tell you what action you should take. And that's what a policy is. A policy, very simply, is nothing more than a function that tells you what action to take in any state you happen to come across.
Okay, but the question that you asked before was about up, up, right, right, right.
Mm-hmm.
And it seems like because of the stochastic transitions, you might not be in the same state. Like you don't know what state you're in when you take those actions.
No. So one of the things for what we're talking about here for the Markov decision process is there are states, there are actions, there are rewards. You always know what state you're in, and you know what reward you receive.
So does that mean you can't do up, up, right, right, right?
Well, the way it would work in a Markov decision process, so what you're describing is what's often called a plan. You know, it's tell me what sequence of actions I should take from here. What a Markov decision process does and what a policy does is it doesn't tell you what sequence of actions to take from a particular state. It tells you what action to take in a particular state. You will then end up in another state because of the transition model, the transition function, and then when you're in that state, you ask the policy, well, what action should I take now?
Okay.
Right. So this is actually a key point. Although we talked about it in the language of planning, which is very common for people who, for example, taken an AI course, to think about this in terms of planning. What are the things that I can do to accomplish my goals? The Markov decision process way of thinking about it, the reinforcement learning way of thinking about it, or the typical reinforcement learning way of thinking about it, really doesn't talk about plans directly, but instead talks about policies, from which you can infer a plan. But this has the advantage that it tells you what to do everywhere, and it's robust to the underlying stochasticity of the world.
So is it clear that that's all you need to be able to behave well?
Well, it's certainly the case that if you have a policy, and that policy is optimal, it does tell you what to do no matter what situation you're in.
Okay.
And so if you have that, then that's definitely all you need to behave well.
But I mean, could it be that you want to do something like up, up, right, 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 which you can't write down as a policy?
Why can't you write that down as a policy?
Because the policies are only telling you what action to do as a function of the state, not like sort of how far along you are in the sequence.
Right, unless, of course, you fold that into your state somehow. But that's exactly right. I mean, the way to think about this is the idea of coming up with a concrete plan of what to do for the next 20 time steps is different from the problem of whatever step I happen to be in, whatever state I happen to be in, what's the next best thing I can do? And just always asking that question. If you always ask that question, that will induce a sequence, but that sequence is actually dependent upon the set of states that you see. Whereas in the other case where we wrote down a particular policy, you'll notice that was only dependent upon the state you started in, and it had to ignore the states that you saw along the way. And the only way to fix that would be to say, well, after I've taken an action, let me look at the state I'm in and see if I should do something differently. But if you're going to do that, then why are you trying to compute the complete set of states? Or, the complete set of actions that you might take.
Okay.
Okay, so there you go. Now, a lot of what we're going to be talking about next, Michael, is given that we have MDP, we have this Markov decision process defined like this, how do we go from this problem definition to finding a good policy? And in particular, finding the optimal policy.
That makes sense.
Good. And there you go.